want to start this topic by reviewing the three reactions of acids that we have seen in the previous topic, and we did the experiment on these three reactions. The first one is the reaction between an acid and a metal hydroxide, and the example I'm using here is hydrochloric acid and sodium hydroxide, and the products are sodium chloride and water. You can detect this reaction happening by using a pH indicator. We use bromothymol blue in the experiment, but you could use other indicators as well. As the reaction progresses, there will be a change in the pH of the solution that can be detected by a color change. Now, if I were to write the ionic equation for this reaction, it will be hydroxide ion, or OH minus, reacting with hydrogen ion, or H plus, to produce H2O. So what is happening here is a flow or a transfer of hydrogen ions. The hydrogen ion has gone from the acid to the base so that it can be combined with the base, the base in this case hydroxide ions, to produce water. So acid, or maybe if we focus on the hydrogen ions, then H plus is transfer from the acid to the base. So you can see that this is an acid-base reaction because it is characterized by a transfer of hydrogen ions, and it produces H2O. So this is the first example. The second example, this is not, I don't think we did this reaction. We did the calcium carbonate version, which was marble chips, but this would probably give you something very similar. So if you mix a metal carbonate with hydrochloric acid, the reaction will produce a salt, in this case sodium chloride, and carbon dioxide and water. So you will be able to detect that the reaction is happening because there will be bubbles, gas bubbles being formed. And the gas bubble in this case would be carbon dioxide, which if you mix that gas with lime water, it's going to turn lime water cloudy. So this was the second experiment that you did. Turn lime water cloudy, and only only carbon dioxide can turn lime water cloudy. So if you want to distinguish or know for sure which gas is being produced, you could use lime water for that purpose. Once again, if I write the ionic equation for this reaction, I will have carbonate ion, or calcium CO3 2 minus. I need to stop saying calcium. Reacting with hydrogen ion to produce. Now, there is actually an intermediate that is not written here. If you combine hydrogen ions with carbonate ions, you are supposed to get H2CO3. It's just that H2CO3, or carbonic acid, it's a very, very unstable substance that would immediately decomposes into CO2 and H2O, which are the two products that you actually see. So even though you don't technically see H2CO3, just keep in mind that this reaction also involves a combining of hydrogen ions and carbonate ions. So I can still say that the hydrogen ion has been transferred from the acid, which is hydrochloric acid, to the base, which is carbonate ions. So H plus is transfer from the acid to the base. So both examples are examples of acid-base reactions, which is characterized by a transfer of hydrogen ion. Now let's look at the last one. So the last one is the reaction between magnesium and hydrochloric acid, and it produces magnesium chloride, or salt, and hydrogen gas. And you can tell that hydrogen gas is being produced. First of all, you can tell that a gas is produced because of the gas bubbles that would appear as you add the piece of magnesium into the acid. But also, if you use a pop test, you can tell that the gas is indeed hydrogen. I'm sure everyone knows how to conduct a pop test at this point. Once again, I'm going to write the ionic equation for this reaction, and I would have magnesium reacting with H plus to produce magnesium ion and hydrogen gas. So hopefully you can see how this reaction is different from the other two, in that I can't say that the hydrogen ions have been transferred from the acid to the base. Clearly, these two reactants don't combine to make the products. You have two completely separate products that are definitely not formed via decomposition. What what looks like has happened is that the magnesium has gone from being neutral, so having no charge, to having a charge of 2 plus. Now, in order for something to become a cation, it needs to lose electrons. So what looks more likely to have happened in this case is that the magnesium has gotten rid of 2 electrons and give 2 electrons to the hydrogen ions. So the magnesium lose 2 electrons to become magnesium 2 plus, and these 2 electrons are accepted by the hydrogen ions so that the hydrogen ions can form hydrogen gas. So this is an example of a completely different type of reaction compared to the other two. Instead of having a transfer of hydrogen ions or a transfer of proton, you have a transfer of electrons. And a transfer of electrons is the definition of a redox reaction. So you actually have done one redox reaction. It's just that I haven't told you that it was a redox reaction. All right, so this is a definition of a redox reaction. A redox reaction is a chemical reaction that involves a transfer of electrons. That is simple as that. And then everything will come from that definition. So generally speaking, if you want to have a successful transfer of electrons, you need to have something that giving away the electrons, and you need to have something that is willing to take the electrons. So it is very similar to an acid-base reaction, which something donates hydrogen ions, something else accepted. The same thing is happening here. It's just for electrons. So there are two. The only other interesting thing about this process is that there are names for each of the processes. So redox reaction involves a transfer of electrons. There are two processes. The first one, well, I wouldn't say that one happens before the other. They're supposed to occur simultaneously. One substance will donate or give away the electrons or lose the electrons, and the process of losing electrons is called oxidation. Some of you may have heard of the term oxidation before in some other context, but oxidation in the case of chemistry refers to the process of losing electrons. And at the same time, some other substance has to receive the electrons. So the process of gaining electrons is called reduction. Now, you may think that the name is a little bit paradoxical, but it really isn't, because when something gains electrons, there will be a reduction in the charge of that substance because electrons are negative. So if you gain something that's negative, you'll be reduced, if you will, or the charge will be lowered. So just remember reduction because charge has been reduced. So that leads me to the very first. There are only two acronyms I normally use in this topic, maybe three, but this is the first one. And it's the mnemonic oil rig. Oxidation is loss of electrons, reduction is gain of electrons. So oil rig hopefully will give you a easy way to remember the definitions or which is which. So oxidation, you're losing electrons. Reduction, you're gaining electrons. All right, so if we summarize that, let's say I have a reactant. That reactant will give away electrons. So the process of losing electron is oxidation. Oil, oxidation is loss of electrons. And something else is going to pick up that electron, and that is reduction. The process of gaining electron is called reduction or rig, oil rig. Now this is where it gets a little bit confusing. I mean, if you think about it, it's not, but it's a little bit weird for some people. The oxidation is the process of losing electrons, but the substance that undergoes oxidation is called the reducing agent. Or reductant is another name that you might have heard of. So a reducing agent, this is a definition of the reducing agent. The reducing agent is a substance that causes something else to undergo reduction or causes reduction. and it itself undergone oxidation. So the reducing agent would lose electrons and undergo oxidation, and it goes without saying, the oxidizing agent would gain electrons and undergo reduction. So the process and the name of the substance are opposite of each other. The reducing agent undergo oxidation. The oxidizing agent undergoes reduction. All right. So you can think of the reducing agent as like the redox equivalence of an acid. So an acid loses hydrogen ions, and a reducing agent would lose electrons, and an oxidizing agent is the redox equivalence of a base. So if a base accepts hydrogen ions, an oxidizing agent would accept electrons. So it's quite similar. Something has to give for something else to take. They just have confusing terminologies. I'm going to go back to this example just to show you what that looks like. So if I have Mg plus 2H plus going to Mg, sorry, I'm just going to do the half equation. Oh yeah, Mg2 plus, sorry, not half equation, ionic equation, and H2. So this is the ionic equation earlier, and we have established that in order for this to happen, the magnesium must get rid of 2 electrons and donate the 2 electrons to the hydrogen ions. So the magnesium would got rid of 2 electrons, and those 2 electrons would be accepted by the hydrogen ions. So in this case, the magnesium is the reducing agent, and the magnesium would undergo oxidation. And you can tell that it has lost electrons because the charge of magnesium has gone up. It has gone from 0 to 2 plus. So undergo, hang on, let me just write this full sentence. It is the reducing agent, and it undergoes oxidation. And then at the same time, the hydrogen ions has received electrons, so it is the oxidizing agent, and it has undergone reduction. Okay, so for now anyway, we're gonna scale this up a little bit, but for now you can detect a redox reaction as well as which substance is the oxidizing agent and which is the reducing agent just by looking at the change in the charge of the substance. So if there is an increase in charge, like going from 0 to 2 plus, then that signifies that something has undergone oxidation by losing electrons. If there is a decrease in charge, then that substance has undergone reduction by gaining electrons. So that's that for this introduction, and let's just have a look at the practice questions and see whether you can determine the oxidizing and reducing agent for these examples. And there is one that I want to point out here, which is the introduction video. This is the process of corrosion or rusting, which is one of the many examples of a redox reaction in real life. I think pretty much all things that are useful are probably, well, not all, but the majority of things that are useful are redox reactions, and we'll look at some other important redox reactions later. But that's all for this video. Thank you.